Okay, 4, 5, and 6 are going to be chi-squared goodness of fit tests. It says, executives at the Thinking Channel have decided to test whether the educational backgrounds of the channel's viewers are different from the educational backgrounds of American adults ages 25 and over as a whole. The executives have following information on the American adult population as a whole, obtained from a recent U.S. current population survey. The highest degree earned, if they had less than a high school education, 12%. If they have less than a high school education, 12% of the people surveyed. A high school education, 25%. College education, 55%. Higher than college, which means they have a master's or a doctorate, 8%. So, the executives also obtained from telephone surveys on the highest degree for a random sample of 150 American adults who are Thinking Channel viewers. These data are summarized in the first row of numbers in Table 1 below. These numbers are the observed frequencies in the sample of 150 for each of the degree categories. The second row of numbers in Table 1 gives the expected frequencies under the assumption that the distribution of highest degree earned by Thinking Channel viewers is the same as the distribution of highest degree earned by the American adults as a whole. So they're going to use these same percentages. They're going to assume they're the same. The bottom row of numbers in the table gives the values, and they're using this calculation right here. The observed frequency minus the expected frequency, and I'm going to square that and then divide it by the expected frequency for each degree category. Fill in the missing values in Table 1, then using a 5% level of significance, perform a test of hypothesis that the distribution of the highest degree earned by Thinking Channel viewers is the same as the distribution of the highest degree earned by American adults as a whole. Complete Table 2, which happens to be on the next page because all of this wouldn't fit on one page. Round your responses for the frequencies, expected frequencies in Table 1 to at least 2 decimal places. Round your responses for this calculation here in Table 1 to 3 decimal places. Round the responses in Table 2 as specified. So I'm going to move this up a little bit because we really don't need the word problem to fill in the table, except we need to know these values here. So I'm going to rewrite those values down here once I move this. So, on my table, up on the top, in that other little table, it said 12% were in this category, 25% was in this category, 55% was in this category, and 8% is in this category. Now for a bunch of these, they've already figured it out. If I take 12% of 150, if I grab my calculator, 0.12 times 150 gives me that's what I'm going to figure out. The number I want in my table. So, here is the observed frequency, I should say. The ones they had figured out were these ones. These are the observed ones. These are they're going to use on their percentages. So here, the one they have figured out, 25% of 150. If I take 0.25 times 150, there's my 37.5. 55% of 150. 0.55 times 150, there's my 82.5. So they fill these two in, we want to fill these two in. So in order to fill those two in, here we're going to do the 12% of my 150. I want to know what 12% of 150 is. That's what my expected value would be. 12% times 150, 18. So there should be an 18 in that box. And on the end, we only had 8% of 150. So 0.08 times 150 is my calculation for that box. 0.08 times 150 gives me 12. So, my observed were that 12 people were in this category. My expected at 12% means I thought there were going to be 18. Here my observed was 35. Based on 25%, I would have expected 37 and a half people. We obviously aren't going to have a half people, but on my calculation. Here, 88 were observed. Based on my calculation, I would have had 82.5. Once I fill in the expected frequencies by taking my percent times my total, now I'm going to do this calculation right here. So, on the first box here, it says I'm going to take f sub 0, which is 12, minus f sub e, which is my 18, squared, and I'm going to divide it by the f sub e, which is 18. So 12 minus 18 squared divided by 18 is what I'm going to do. And if I do that calculation, I should come up with a 2. Same thing through this box here. Going to use this formula here. So my observed is 15. I'm going to subtract my expected. I'm going to square that, and I'm going to divide it by the expected. Here, when you calculate that, 15 minus 12 squared divided by 12 gives me 0.750. Second page of that. We have to pick out what is the type of the test statistics. Well, according to the name of the directions, we hopefully already know, we are going to do the chi squared, which is the one that looks like this. We also probably have to figure out the degree of freedom. The degree of freedom on this one is how many different categories we have minus 1. So, the degree of freedom is the categories, the number of categories minus 1. Here we have 1, 2, 3, 4 categories. We have 4 different things. So 4 minus 1 would give us 3, so our degree of freedom is going to be 3. To find the value of your test statistic, this value right here, we're going to add all the numbers in the bottom row up here. So the bottom row was the f sub 0 minus the f sub e squared divided by f sub e. So I'm going to take each of these values and just add them up. So I'm going to take 2 plus 0.167 plus 0.367 plus 0.75. Add those 4 numbers together. If I add those together, I get 3.284 for the value of my test statistic. Now I'm going to do a p-value test. We've done all those testing. We're going to do the p-value test. This is a positive number, good thing, because we like to do p is greater than. P of chi squared is greater than our test statistic, 3.284, with a degree of freedom of 3 is what we figured out. So again, we have to do that on the Alex calculator. P of chi squared, that's how that's pronounced. It looks like x squared, but it is chi squared. P of chi squared is greater than 3.284 with a degree of freedom of 3. We should get 0.350. Tells us to round to 3 decimal places. So we like to show that third one even though it's a 0. So now we're comparing our p-value. to what we wanted to compare to, which on the top, or actually we can see it right here, said we were going to do a 5% level of significance. So, is 0.350 greater than or less than my 0.05? Well, we can obviously see that it's greater, right? 3.5 is greater than 0.05. So, as we did before with the p-values, if my percentage is greater than my level of significance, we want to accept, accept the null. We're going to accept the null. So, they didn't have us write what our statements were. So again, if we were doing our test statistics and it on here, when we did the null we know is going to be equal. The alternative one means it's not equal. The question asks, can we conclude that it is different? Can we conclude it's different? Well, in this case, this is the true statement. This one is not true. The null means it would be equal. The alternate ones, it's not equal. And so can we accept that it's different? Can we accept that it's different? No, because we said it has to be equal. They skipped the step where they had you write the null and the alternate hypothesis because they probably figured by now you knew how to do that. So the null will always be the equal, the alternative one will be not equal. So if it asks me if it's different, I would see, is this one true? No, it's not. That one is not true. All right. So, number 5. Matrimony Monthly is a top-selling magazine that provides information for couples thinking about marriage. Over the years, writers for the magazine have researched just about everything there is to research about weddings. The popular conception at the magazine has been that roughly 50%, we're going to need these percents on our table, of first weddings take place indoors in a church. 30% take place in a building other than a church. And 20% are outside, are outdoors. This past week, the magazine examined a random sample of 250 first weddings and found the distribution given in the first row of numbers in the table below. This row contains the frequencies observed in their sample of 250. The second row of numbers in the table is the frequencies expected based on those percentages under the hypothesis that the popular conception at the magazine is correct. The bottom row is where we're doing our calculation for each of the wedding categories. Now there's some disagreement among employees of the magazine. Some say this sample demonstrates that the actual location distribution of first weddings is different. So again, we're checking different, and so we're checking equals and not equals from that in the magazine's popular conception. Others maintain the sample data according to the magazine's population conception that any differences between the two are due to chance. Fill in the missing values from Table 1, then at a 5% level of significance, perform a test of hypothesis, that is the actual distribution of first wedding locations, matches the distribution in the magazine's popular conception. Complete Table 2. So, going down here, again, we need those percentages, so keep that page handy when you slide down to this table. So, when I get to that table for problem number 5, first thing I'm going to do is write my percentages on top. According to the magazine, 50% were in this category, got married in the church, 30% got married inside but not in the church, and only 20% got married outside when they had their first wedding. So here are the observed data. We want to fill in the expected ones. They already filled this one in for me. If I took 30% of 250, it is that number 75. You could calculate it and find out. 50% of 250 then goes in this first column. 50% times the 250 total, right? 50% of 250 means I would have 125 in this section. For the outdoors we said 20% is our expected, so 20% of our 250, 20% times 250 means we would have expected 50 to be in this category. So now we're going to fill in the calculation from our formula. Again, they already did this one for you. You could calculate it out and see that you do get that same number. They did one of the boxes trying to make it a little shorter. So, observed frequency 141 minus the expected frequency 125 divided by the expected frequency 125. That's my calculation for that box there. Oops, I forgot the squared. Right, it's supposed to have that squared there. 141 minus 125 squared divided by my 125. If you punch that into your calculator, you should get 2.048. 2.048. On my other one, I'm going to have my observed frequency of 49 minus my expected frequency of 50. I'm going to square that and divide it by the expected frequency, which is 50. So 49 minus 50 squared divided by 50 should give you 0.020. 0.020. Again, because it says to go to 3 decimal places, I like to put the 0 on the end, so I'm showing 3 decimal places. The type of the test statistic, again, is going to be your chi squared. The degree of freedom. Your degree of freedom, how many categories you have, minus 1. In this case, we have 1, 2, 3 categories. Either they got married in the church, indoors but not in the church, or outdoors. So 3 minus 1 is 2. We're going to have 2 degree of freedom then. Chi squared with a degree of freedom of 2. We are going to then find the value of our test statistic. To find the value of the test statistic, we're going to add all the values for the calculation, which means add all these ones in this bottom row. So I am going to take 2.048 plus 3.000 plus 0.020. We only had 3 columns this time, so we're going to add up those 3 numbers. So if we add up those 3 numbers, we get 5.068. 5.068. So we are now on this one going to do the critical value for our test. When we do the critical value, we're not doing the p-test, we're doing the chi squared test. So we are going to do chi squared at the 0.05 level of significance with degree of freedom of 2. So on this case, if you calculate that out using your Alex calculator, if you haven't done that already, just giving you a second to get that punched in. Chi squared at the 0.05 level of significance with a degree of freedom of 2 should give you 5.991. So when I'm testing this one, My critical value is 5.991. I am trying to figure out if I'm in my null section or my alternative section. Again, on my null, the null is the equal to, the alternative one is the not equal to. In other words, does it differ? Is it different or not? So if I check my test value, is my test value smaller or bigger than 5.991? Well, if I look at that, my test value is 5.068. 5.068 would be smaller than 5.991. So I have to do the null because I'm in the section for the null. I have to say that it's equal. Can we conclude that the actual distribution is different? No, I have to say it's equal. It is not different. And so no, I cannot conclude that it's different from the distribution in the magazine. Number 6. Same kind of thing here. Depression and insomnia often go hand in hand, and sometimes it is unclear which of the two should be the primary subject of treatment in an individual suffering from insomnia. Mendoza and Company, a national pharmaceutical firm, has positioned itself as a specialist in the production of both antidepressants and sleeping pills. Mendoza's current business model describes the following breakdown of Americans: approximately 50 million adults suffering from insomnia. 17 use both antidepressants and sleeping pills regularly. 24% use only antidepressants, and 15% use only sleeping pills. The remaining 44% use neither antidepressants nor sleeping pills. So in a recent issue of the Psychiatry Journal, Patterns contained a study on insomnia. In the study, 180 Americans suffering from insomnia, but otherwise chosen at random, were asked about their use of antidepressants and sleeping pills. The breakdown of their answers is given in the top row of Table 1. These numbers are the frequencies observed from the sample of 180 people. The second row in the table is your expected frequencies based on our percentages under the hypothesis that Mendoza's model is correct. The bottom row contains the value that we get when we do our calculation. The observed frequency minus the expected frequency squared divided by the expected frequency. So again, we're going to fill in our table and then answer our questions. And so I'm going to move my table here. Whoa, I jumped all the way to number 4. So on number 6, again, I'm going to slide up this high so we can see both of our tables, but we need to fill in our percentages. And so again, if you go back to the reading, 17% used both, it says. Only antidepressants, if I go to my reading, 24%. Only sleeping pills, 15%. And the remaining 44%, it said, used neither. So again, we're going to do our calculations. Here's the observed data. What is our expectation based on these percentages? Here, these two are filled in. 15% times 180 is 27. 44% times 180 is 79.2. We want these ones. So here, 17% times our 180. If you do 0.17 times 180, you should get 30.6. And then our other one, 24% of 180, so 0.24 times 180. 0.24 times 180 is 43.2. Then they're going to do our calculations here. So my observed frequency, 40, minus my expected frequency, 30.6. This time I'm going to remember to square it, divided by the expected frequency, 30.6. So in parentheses, 40 minus 30.6, then that's squared, and then I'm going to divide by 30.6. And on all these, we're rounding these to 3 decimal places in the bottom row. So we're going to use 2.888 is what we get for our answer. On our other one, our observed was 30 minus our expected, 43.2 squared, divided by the expected, 43.2. So in parentheses, 30 minus 43.2 divided or squared, and then divided by 43.2. We should come up with 4.033. 4.033. So again, on the second table, if we go over to that second table, wants to ask us about the type of test statistic. We know it's chi squared. On our degree of freedom, the number of categories minus 1. We have 1, 2, 3, 4 categories. So 4 minus 1 is going to give us 3. 4 minus 1 gives us 3. So we have 3 degrees of freedom. So the number of categories minus 1 is your degree of freedom. We had 4 different categories. 4 minus 1 is 3. Value of our test statistic. When we find the value of our test statistic, we're just going to add this whole row together. And so we had 4 different values. 2.888 plus 4.033 plus 1.815 plus the last one, 1.473. So we're adding all the values in that row to get the value of our test statistic. If you add all of those together, you get 10.209. It says round to at least 2 decimal places, which I didn't follow my directions, so 10.21 would also work. But again, it says at least, so if you go farther than 2, it's going to count it correct, it knows. Then we're going to do the p-value on this one. So for our p-value, again, we're testing here between the H0 and the H1. We're going to do p of chi squared is greater than that value, 10.21. And again, you could use 209. P of chi squared is greater than the 10.209. Oh, I forgot my degree of freedom. You'll know, it'll tell you when you type that in on the Alex program. I always am forgetting to write that down for you. But it asks for the degree of freedom, which is 3. So my p-value to 3 decimal places, 0.017. 0.017. So 0.017. We want to compare that to a 10% level of significance, 0.01. 0.017 is just a little bit bigger than 0.01, right? Oh, never mind. I'm not doing 0.01. Ignore me. I'm gone crazy. That does not say 0.1. It says 10. 0.10. So 0.017 compared to 0.10. 0.017 is less than 0.10. Since that is less, my percent here is less than this, we are going to reject the null. Now again, we have to remember that the null is the equal, the alternative one is not equal. So we're rejecting the null. This is not true, which means this one is the true statement. Rejecting the null, we're rejecting that it is equal. That means it's not equal. Can we conclude that the percentages given in the model are incorrect. Can we say they're incorrect? Yes, we can, because they are not equal. That is my true statement.